Today we'll be talking about electron geometry, molecular geometry, and bond angles. So I alluded to this in the last video. I said something about VESPER and some of you are like, what is that? It is this lovely acronym. So what does that stand for? It stands for valence shell electron pair repulsion, and this is actually a model. So this is taking a look at, it models the geometry of a molecule by minimizing the repulsion between electron pairs. Alright, so the VESPER model is basically taking the geometry that will allow for those electrons to be as far apart from one another as they can be. Right? Think about those negative ends of a magnet. They don't want to be very close to each other. They want to be far away from each other. The same is going to be true for these electron pairs. So there's certain geometries that they take in order to maximize that that separation between them, or the distance, between them. So we're going to go through a few examples. So we're going to start with, and I put in some pictures so that way they're better pictures than what I would draw. So let's start with beryllium chloride. So if you recall, beryllium's one that is happy with only 4 electrons or 2 bonds. We put it in the center because chlorines are halides. They will be on the outside. They can only have 1 bond. If we look up at our periodic table, which yes, I do have, let's count how many electrons we have. Beryllium has, it's right here. We have 2 valence electrons we're working with. Chlorine's over here, and it has 7, because remember, 1, 2, 3, 4, 5, 6, 7, and 8. So beryllium has 2, chlorine has 7. So if we were to add that up, we have our 2 plus our 7, but remember we have 2 chlorines, so we have to multiply that by 2. Okay, so we end up with 14, 16. So if I distribute my electrons down, I already have 1, 2, 3, 4 from the bonds. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Woo! The chlorines have the octet rule satisfied, and beryllium, remember, only wants 4. So we're good. This looks like this. So this is going to be electron pair geometry and the molecular geometry. They're going to be the same. And I'll talk about what the differences are between those two when we get to an example that shows that. But for these first few, they won't be different. Okay, if we look at the distance between this atom and this atom, it's 180 degrees because it's linear, right? It's in a line. So both the molecular and the electron pair geometry are going to be linear with an angle of 180 degrees. And that makes sense, right? The furthest apart these other electrons, so those bonds, can be from one another are going to be at the exact opposite ends, which is going to be 180 degrees separate from one another. Let's look at another one. Okay, so let's look at boron fluoride. So let's count up those electrons. Erase the ones we did last time. All right, we are looking at, we got boron here. Fluorine is here, so 3 and 7. So 3 valence electrons plus 7, but remember we've got 3 of them, so we need to multiply that by 3. This gives us 24 valence electrons to work with. We're going to put our boron in the center, and then we attach our fluorines. All right, I've used 6 electrons so far. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Used all my electrons. The fluorines all are satisfied with the octet rule. And remember, boron is happy with only 6 electrons. For this configuration, the furthest apart these atoms are able to get from one another is going to look like this one here. And this angle is 120 degrees from one another. So the angle, the bond angle, is 120 degrees. The name for this structure is called trigonal planar. Okay, if you think of a plane, it's in one plane, right, in 3-dimensional space. A sheet of paper would be kind of like one plane. It all can fit on that flat sheet of paper. So it's one plane, which is why it's planar. Trigonal because there's 3 points coming off that central one. Molecular geometry is going to look the same, and therefore it's also called trigonal planar. Next, let's look at CH4, methane. Alrighty, we've drawn methane a few times, so I'm just going to draw it out for you here. Okay, this is what the Lewis dot structure looks like. The Lewis dot structure previous to have been very good at showing us, oh yeah, that makes perfect sense for how it's going to look. It looks just like, well, pretty darn close to our electron pair geometry and our molecular geometry. But when you get to these higher numbers in your molecule, it's going to look a little different. So you can see it kind of looks like a pyramid. That carbon is in the center, and the way that the hydrogens can be furthest away from one another is in this conformation, where it kind of looks like a pyramid. Or we call this a tetrahedral. And I guess we wouldn't call this a pyramid because pyramids have 4 sides. It's flat, and then it's got the 4 sides that are coming up. This only has 3. All right, the molecular geometry is going to be the same again. So it's also a tetrahedral. The difference in angles here, this is 109.5 degrees. And it's going to be the same for all of these. And that's how they maximize their distance away from one another. And I will show you this a little bit more maybe with a balloon demonstration in person. Or as in person as we can be online, right? All right. Next, let's look at phosphorus. I'm blanking the word for 5 for chloride. I'll probably get there as soon as I start drawing things out. So, we all have our brain farts, right? So our phosphorus pentachloride is drawn out like this. You can go through and add up your electrons. If we find phosphorus on the periodic table, it's right here, and our chlorine is right here. So we've got 5 and 7 valence electrons for each there. So for phosphorus, we said we had 5. Chlorine, we said we had 7. We've got 5 chlorines, so we need to multiply by 5. This will give us 40 electrons, valence electrons to distribute. If you count it all up, it will look like this. This is 40 electrons. Now, the shape of this gets quite interesting. If you take a look at this image here, so look back at the trigonal planar. Remember, this was just all flat in one place. That was the way to get them most easily separated. These chlorines are going to, and these phosphorus are going to be just like the trigonal planar. And then we have these chlorines going directly up and down kind of linearly with the phosphorus, and this will maximize our distance between them. So this is called, still going to be trigonal because it has that trigonal shape in that center, but it's going to be called Pyramidal, because it's kind of, if you look at it, it's kind of like two pyramids that got stuck together, right? You've got one pyramid down here and one pyramid up here. So that's one way you can kind of remember the name of it, right? Trigonal bipyramidal. This is going to be the same drawing for our molecular geometry, and therefore it's also called trigonal bipyramidal. Looking at the bond angles, remember for the trigonal planar, we said that these are going to be 120 degrees apart. That's true. But the ones that are going up and down, this is going to be 90 degrees. So it has two different bond angles. It's got 90 degrees and 120 degrees. All right, so far we've done everything where the electron pair geometry and the molecular geometry are the same. Now let's look at a couple where they're not. So an example of that would be ammonia, which is NH3. Okay, if we look up at our periodic table, nitrogen has 5 valence electrons, and we're working with hydrogen, which has 1. So that would be 5 plus 1, and then we've got 3 hydrogens, so we need to multiply that by 3, and this will give us 8 valence electrons to distribute. I start by putting my hydrogens on to my nitrogen. That uses up 6 of my electrons. I've got 2 more, so I'll put it on my central atom here. So that way my nitrogen's satisfied with the octet rule, and the hydrogens, remember, only want 2 electrons next to it, so they're happy. So this is my Lewis dot structure. Now the way that this looks is that you're going to have, it's very similar, if you recall, to, let's look back up here, tetrahedral, right? Except for this top one, this top hydrogen, instead wouldn't be hydrogen, it's going to be a lone pair. Right, this is our 2 electrons up here. Kind of looks like a fun little guy with eyeballs now. Woohoo! Okay, so it's going to look like this for its electron pair geometry. This electron pair geometry, because it's the same looking, remember it's got, if I were to draw this out, it looks like, oops, it looks like the tetrahedral. It's the exact same. So this is tetrahedral. Now, where electron pair geometry and molecular geometry differ is electron pair geometry includes those lone pairs. And then it's going to shape. You need to look at this in order to figure out, you need to do electron pair geometry first, figure out, okay, the lone pair is going to push these other ones down this way, giving it a tetrahedral shape for its electron pair geometry. But the molecular geometry is looking at it as if we don't see any of those electrons. All we're seeing are the nuclei for each of the atoms in the molecule. So looking at that, what's left, you're still going to have that same shape down here, but you're going to lose the lone pair electrons. So this is going to leave it with a pyramidal shape. So now you can see how those differ. So anytime you have a lone pair of electrons, you will have different electron pair geometry than molecular geometry. So keep that in mind. Anytime you have a lone pair, they're going to be different. If they're not, if you don't have any lone pairs, then you don't need to worry about it. And this is lone pair on the central atom. Okay, we're not talking about any of these other atoms that are around it, right? The chlorines have all these lone pairs around it, but that's not what we're looking at when we're looking at the overall geometry of these molecules. We're looking at just the central atom, okay? All right, so the angles are a little different. These lone pairs actually, because there's no positive aspect to it, it's only negative. This is very negative, right? Because it's only electrons. So it's actually going to repel these other ones more so than if it were just another hydrogen. So then this bond angle is going to be quite a bit bigger, making these other ones squish together quite a bit more. So these will be less than 109.5, and it varies, and that's why we just leave it as less than 109.5. Not going to make you memorize further than that. So just remember, tetrahedral, it's 109.5, but when your molecular geometry is pyramidal, it's going to be just less than 109.5 degrees. Need to put the degrees in there. Alrighty, let's look at another one. Let's look at water. Good old water. So if I do the Lewis dot structure for this, it looks something like this. You've also probably seen me draw it out like this. Both are fine. The reason why I draw it out like this lower one typically is it does a better job representing what the actual molecular geometry ends up looking like, but this top one is perfectly acceptable. All right, so you can see we've got two lone pairs this time. We got two lone pairs. So they're both going to take up, again we have, this is going to be tetrahedral. For the electron pair geometry, because it's got four things coming off of my central atom. Tetra being 4, so that's one way you can remember. If you have 4 things coming off your central atom, including lone pairs, the electron pair geometry is going to be tetrahedral. All right, now 2 of these are lone pairs, so what's left is going to be this funky bent shape for our molecular geometry. So we actually just call this bent. And its angle, similar to the extra push that you have for the pyramidal, will also be, less than 109.5 degrees. And like I said, I'm not going to make you memorize further than that. Alrighty. Let's look at one more example. I'm going to switch back to blue. I like blue. So for this example, we're working with sulfur and 6 fluorines. Let's look at how many valence electrons we're working with. So sulfur is right here, so it's got 6 valence electrons. And fluorine is over here in the halides, so it's got 7. So 6 valence electrons plus 7. I've got 6 of those fluorines. Okay, so this will give me a total of, oh goodness, give me 1 second. Find my calculator, because apparently my brain doesn't want to do simple math. I'm sure some of you are like, oh, come on, Dr. Ricker. I got this. All right, 48 valence electrons that we're working with. We would distribute them around that central sulfur atom because these fluorines are not able to. So this is an expanded octet. The fluorines are not able to form more than one bond, so they're all going to have to attach to that sulfur. Let's see, 1, 2, 3, 4, 5. There's all my fluorines attached to my sulfur. Now I can distribute my electrons. So I've done 1, 2, 3, 4, 5, 6. So that's 12 electrons already used. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Shoo! All right, all the fluorines have their octet rule satisfied. Sulfur is going to be our expanded octet. And so it looks like we are good. We've distributed the valence electrons well. Its molecular geometry looks like this. And we call this an octahedral. And because there's no lone pairs on that central atom, for our molecular geometry, it's going to be the same. So we're also going to call it an octahedral. Now, its bond angles, similar to when we were looking at the trigonal bipyramidal, we're going to look at the bond angle here is going to be the same. Oh, wait, no, it's not going to be the same as that one. Ha ha ha. Silly me. All right, well, let's first look at this one. This one's going to be up and down 90 degrees, right? Okay, this is this one that's in the plane. We've got 4 that's going to be in this plane coming off of this sulfur. That, if you think about, we've got 160, the furthest they can be away from each other, or sorry, not 160, 360. The furthest away they can be away from each other is going to be 90. Oops, I still have eraser on. Here we go. Also 90 degrees. So our bond angle here is 90 degrees. All right, so we've talked a lot about Lewis dot structures, right? That's what all these in this column have been. We've talked about, so these that I've drawn, or that I've put in pictures, these are called ball and stick models. So far you've seen Lewis dot structure models. Let's actually write that in. And you've seen ball and stick models. There's a third model I just want you to be familiar with, and that's these space-filled models. And they look like these. So this first one up here, this one's linear. And basically, if you had the ball and stick, it would look like this in it, right? It's basically just filling the space with where those electron clouds would be. This next one would be, these would be our points. And this would be trigonal planar. And then this last one would be an example of what a, I can't really draw the ball and stick over it. This would be an example of what a tetrahedral would look like. I guess I'll write them all in. Trigonal, planar. All right, so that's what I've got for you today. Hopefully you're feeling comfortable with the difference between the electron pair geometry and molecular geometry. Remember, the biggest difference between the two are, do you have a lone pair on that central atom? If you do, your electron pair geometry and your molecular geometry are going to be different. If you don't have a lone pair, those two will be the same. All right, time to go practice.